In this video, we're going to talk about what is referred to as the enthalpy of a reaction. So we've already defined enthalpy as being equal to Q, or the heat of a reaction at constant pressure. So in common terms, we sometimes refer to the enthalpy of a reaction as the heat of reaction, because a change in enthalpy is going to be symbolized like this, delta H, and it's going to be the enthalpy of our products minus the enthalpy of our reactants. So this is our equation that we can think of when we think about the enthalpy change of a reaction. We have here an example of a reaction where we have these high energy reactants. We have methane and 2 moles of oxygen gas. So both of these are gases, and they are shown to have higher enthalpy than the products down here. So this would be the reaction going in this direction here. So I have reactants up top and then products down here. And notice that I have this delta H1, this change in enthalpy value here of negative 890 kilojoules. So that's showing that my reactants going to my products are going to be releasing energy in the form of heat in this exothermic process in the amount of negative 890 kilojoules. So whenever we see heat being released in an exothermic process, we expect to see that negative delta H. And then say we looked at this in the reverse, so I'll cross these out. So now these are my reactants. I have CO2 and liquid water, the lower energy reactants. Now we have to add energy, right? So if we're going up here to get to our products, and now that's going to be methane and oxygen, we would have to add the same amount of heat, so delta H of positive 890 kilojoules, to go from CO2 and H2O to form methane and oxygen. So notice that these are reverse reactions, and they are the same magnitude, the same numeric value, but opposite in sign. So some things to talk about, all the other things to talk about regarding enthalpy, is that enthalpy is an extensive property. So if you recall, that depends on how much you have. So it depends on quantity, we can say, in short. So it depends on how much I have. So if I have 1 mole of methane, as we see over here, that combusts with 2 moles of oxygen gas, and then we get 1 mole of CO2 and 2 moles of H2O. But say I had 2 moles of CH4, and then everything else balanced out, including the products. We can look here at this reaction and say if this is a delta H of negative 890 kilojoules per mole. Now, if we have 2 moles, it would be 2 times that quantity, negative 890 kilojoules. So for that reaction, we would see negative 1780 kilojoules. And this tells us that we have a delta H, which implies an exothermic reaction, and it would release this amount of heat. In this other information here, number 2, we can see that the delta H reaction in the forward direction, as I mentioned before, is going to be equal in magnitude, equal in size, but opposite in sign. So we saw that the delta H1, so the original forward direction, was 890 kilojoules for that reaction. The delta H2, the reverse of that, is going to be positive, but the same amount, 890 kilojoules. And these values were shown for 1 mole of methane, but then we could definitely multiply by 2 to get that value above. And now in this third bit of information, delta H of a reaction depends on the state. So the phase, so whether we're solid, liquid, or gas of both the products and the reactants. Because of that relationship that we saw above, where we have the enthalpy of the products minus the enthalpy of the reactants to get the enthalpy change, this is very dependent on phase. So let's see here in sample exercise 3, if we can find out what they're asking for here. They're asking us to calculate the quantity of heat. So the quantity of heat that is released. So this must be an exothermic process. We can make a note about that. And we see that we have a negative enthalpy value in the forward direction here. So that matches up. When 5 grams of this is hydrogen peroxide decomposes, and we're told it's at constant pressure. So that means that we can go ahead and say that Q equals delta H because we're at constant pressure. So that's just a side note. And we know that we have for every 2 moles of H2O2, we release negative 196 kilojoules. So if we were to find out how many moles we had, we could take 5.00 grams of H2O2, and then we're going to divide that by the molar mass, which 2 oxygens are 32, and then we add 2 more, so we have about 34 grams per mole here for our molar mass. So that means that I have this term here that I can use for every 2 moles, this negative 196 value as a conversion factor. And I can say that I release negative 196 kilojoules for every 2 moles. And this term would have been converted to moles because grams would cancel out. So now I want to multiply by negative 196 divided by 2, and that will give me my answer of 14.4 kilojoules. And this is the quantity of heat that is released. So let's see what they ask us to do in part B here. So now we have a negative 502 kilojoules of heat released. We want to know how many grams of O2 were formed. So we're going to use that same balanced equation up here where we have the amount of heat for 1 mole of O2. So we see for every 1 mole, that relationship to the negative 196. So we can say that if we released negative 502 kilojoules, we can use that conversion factor and say that for every 1 mole of O2, we release negative 196 kilojoules. So now my kilojoules cancel out. I am in moles of O2, but I want to be in grams like they asked above here. So I can say for every 1 mole of O2, that's approximately 32 grams. So now I will divide 502 by negative 196. Both negatives will cancel out. Oh, and then I multiply by 32 grams. So if I keep the right amount of sig figs here, I would have 82.0 grams of O2 were formed. And I know that when that's negative 502 kilojoules of heat being released.